Hi everyone, this week we're very happy to have Joe Tooby-Smith telling us about some interesting progress in Hilbert. So whenever you're ready.
Nice. Yeah, so I've kind of gone with a fairly broad title here, Symmetries and Field Theories. Hopefully, as the talk progresses, it will become clearer what I mean by this. Let me start with a few disclaimers. The first disclaimer is that I'm dyslexic, so there are going to be some words and some phrases that I'm going to get wrong during the sentence. If there's anything you don't understand, just let me know and I'm happy to repeat myself. The second disclaimer is that I like to do talks in a slightly different way to perhaps what is traditional. Sometimes this works, sometimes this doesn't work, but if you have any feedback on what you think works and doesn't work at the end of the talk, that's great. The third part of this disclaimer is really about the contents of this talk. I decided to plot my papers versus time and how mathematically rigorous they are, or how much maths compared to how much physics they contain. And as you can see, it's fairly random, the sorts of things that I work on. So down here are the more pheno papers, and up there are the more mathematical papers. Unfortunately, or perhaps fortunately, the paper that I'm going to be talking about today is the one right up there in the pure math section. But hopefully it should be understandable. I hope I haven't gone too far the other way and made it too colloquial. If there are things you want me to explain in a different way, perhaps more colloquially or perhaps more mathematically, feel free to ask me about it. And I'm happy to explain it in a different way. I'd rather give half a talk that half you understand rather than a full talk that none of you understand. So the paper this is based on is this Generalized Symmetries of Topological Field Theories, which was in collaboration with Ben Gripaios, who was my PhD supervisor, and Oscar Randal-Williams, who's a mathematician, both of whom were at the University of Cambridge. I'm going to split the talk into three parts. The first part is going to be about orientation, really what is the contents of this paper, and really where it fits in the main scope or the main broader area, let's say. The second part of the talk, I'm going to look at this thing called abstract nonsense, which despite its phrasing is actually a technical term, meaning category theory. We're going to look at group actions and fixed points, hopefully in a way which is understandable if you've never come across these areas before. The third sub-talk, I want to go back to undergrad, and I want to give you some actual physics contents that you might understand, which is the symmetries of quantum mechanical-like theories, and really we'll try and classify those symmetries. So let's begin with orientation. And really the aim of this first talk is to put what we've done, this paper, in the context of the broader area. And by broader area, I really mean generalized symmetries. So generalized symmetries can be seen to fall into three different parts, or one can classify them in three different parts. The first part is the hep.th part, and this is things like non-vertical symmetries, categorical symmetries, and end-form symmetries. The second part, which is really being pioneered by people here, is the connection with the hep.th part and the phenomenology. We had this paper last week about neutrino masses and the sort of the mass program, and this program next year. So the question is, what's the third part? I'm going to leave this a bit ambiguous for now, and I'll tell you really what this third part is as this first bit of the talk goes on. But to give you some motivation or give you some idea of what this third part contains, let me show you this picture, this screenshot, which is the deep dives of the arXiv page. And you'll notice from my specific version of the arXiv, I've clicked on two of these topics quite frequently, which are algebraic topology and category theory. So you may be asking yourself, why do I click on algebraic topology and why do I click on category theory? Maybe there's a first order question here, which is, what on earth is algebraic topology and what on earth is category theory? So let me give you the one-line definitions. Algebraic topology is the study of homotopy groups, cohomology, topological spaces, and all of that stuff. Category theory, and here I've been slightly more general, slightly more specific about the type of category theory I'm talking about, this infinity category theory, is really about the study of objects and their interrelationships. So you can have, for example, vector spaces and how they are related to one another through linear maps. I don't need you to know any of these two areas to understand this talk. I just want to acknowledge that they exist. And if you've never seen them before, but you've happened to land on this website, the NLab, you will know the NLab is really about using these techniques, homotopy theory, category theory, to understand physics, philosophy, and whatever else they decide to do in there. So when you see certain pages on the NLab, it tends to be within this language. Okay, so that answers the question of what is algebraic topology and what is category theory. Let me answer the question of why am I interested in it? Me naively as a physicist, why do I care about algebraic topology and why do I care about category theory? And this is the reason. While the physicists have been working and messing around with the path integral and field theories, defining, for example, effective field theories, looking at QCD, looking at confinement, the mathematicians, and really I mean the algebraic topologists and the category theorists, have been asking how to do the path integral properly. This is a big area and it's been developed since 1948 when Feynman first wrote down the path integral. And here are like the main developments. Here are the main things that happened in this area along this line. Firstly, we had the definition of a TQFT. So this is really an axiomatic version of field theory. I'm going to flash up the definition. You may not understand it. If you don't, that's fine. Really, these field theories are the simplest types of field theories that you can possibly have. They don't have dynamics. They don't have Lagrangian. They don't have a path integral. There's no action to them. They are very simple field theories. There's no dynamics. And one could argue that there's very little physics there. But they are simple enough that you can write down an axiomatic definition. You can start with the rules of set theory, and you can write down and you can define these field theories in a way that you can't do with normal field theories because of the path integral. And for the experts in the room, I'm restricting myself here to extended topological field theories, which have this property of locality. And that's one of the few physical principles that they do have. The next big development in this area was the cupboardsum hypothesis. And for me, for the purpose of this talk, what the cupboardsum hypothesis says is that the space of TFT, so if you take all of these field theories, you can think of them as a space. That space forms what's called a topological space or an infinity groupoid. They are one and the same thing. So really, this is kind of one of the big theorems in this area. You can ask about the physics behind it. It says some other things about gauging and globalization. But really, these are the two big developments in this area. This definition of field theories, topological field theories, and this definition of this cupboardsum hypothesis, which has partially been proved by this mathematician called Jacob Lurie. An objection to this whole area, of course, is, okay, fine, yeah.
I was wondering how things like level rank dualities fit into interpreting the space of TFTs as a topological space. Is there like some stacky or with forwarding?
Yeah, I don't know. Sorry. I'm not sure what level rank dualities really are, to answer that question. Yeah, okay, so these are really the two big developments in this area. More recently, let me start again. One of the objections you might have with this is that, okay, fine, it's a very axiomatic version of axiomatic way to define field theory. I haven't really told you any of the contents of the definition. I just kind of told you to believe me. You could argue, okay, that's not really that close to physics. It's not close to the physics that we know and love. It's not close to the standard model. So you could ask, okay, are they getting anywhere with that respect? And let me just flash up that mathematicians Texas have been looking at geometric field theories, which is kind of things in the same flavor, but allow you to do more general things, like proper quantum mechanics, like things with fields and things closer to the standard model. So this is really the main development of this algebraic topologists and the category theorists in the area of field theories and defining an axiomatic version of the field theory. So let me go back to this diagram, and let me ask what the third part of the story is. If I have this node, which is the math.at and the math.ct part, really this is the formality, this axiomatic version and axiomatic approach to field theories. And one can ask, what about the connection between this and TH, the non-invertible symmetries, the categorical symmetries, and the end-form symmetries. Can we build that connection? In other words, through topological field theories, what can we learn about symmetries? So this is the question that we asked in this paper. And this is the question that we started, this is the broad scope of things that we started to look at. So let me tell you what we learned. I'm going to give you a lightning overview here. In the rest of the talk, we'll take one specific example, and we'll look at that in more detail. So, the first thing we learned is that an ordinary symmetry is defined through the action of a trivial action of a discrete group on the space of TQFTs. So you have this topological space of TQFTs, and you have a discrete group, and that acts on this, and it moves things around. I'm not expecting you to know all of the words here. Maybe just acknowledge that an ordinary symmetry is through a trivial action of a discrete group. If one wants to define things like projective representations, the thing that changes is that you go from a trivial action to a non-trivial action, and diagrammatically I've changed this so that my points get moved non-trivially, but you still have a discrete group. And if you want to define generalized symmetries, you have a non-trivial action, again like projective representations, but instead of a discrete group, you have a topological group. And this kind of all falls down, this all kind of all comes from mathematics, from the way that people define group actions on topological spaces, how people define group actions in category theory, and how they define it in multiple theory. You can ask a bunch of other questions, we learned a bunch of other things, which I've put here. Higher form symmetries are abelian just because the higher multiple groups are abelian. One can classify these symmetries, and really this is the thing that I'm going to be focusing on for the rest of this talk. One can gauge symmetries using the cupboardsum hypothesis, and you get things like Hooft anomalies, ambiguities, and what we call their metaphysical counterparts. Whenever you see a slide like this about what we learned, you should always ask what we didn't learn. So what didn't we learn by this? We didn't learn anything about nervous theorem, conserved currents, defects, or anything like that. And that's just that these field theories, these topological field theories that we're dealing with, just don't have the geometric structure there that allows you to consider things like Lie groups, or Lie group actions, or smooth group actions. Okay, so this is kind of like the orientation. It's kind of put what I've done in context. And the rest of the talk is really going to focus on this one point of, can we classify symmetries? I could have talked about any of the other points, but just for simplicity and just to give you a concrete example of the material in the paper, I just wanted to focus on this one thing. Okay, so let me just take a second to ask, does anyone have any questions? This is just a random joke that I'll put up when people are thinking if they have any questions. Yeah, does anyone have any questions about the first part?
So when you say can one classify symmetries, are you then restricting to local quantum field theory, Euclidean compact, or something more?
No.
The thing you never mentioned in any of the earlier slides is anything Lorentzian.
Yeah, no, so there's no metric at all on my spacetime. My spacetime are manifolds. So these field theories, they're defined on this category called the cupboardsum category. And that category it's really, you can think of it as the category that gives you your spacetimes. And the structure we have there is we have just the manifold. Sometimes you put orientations on it, sometimes you put framings on it. But something like a metric, like a Lorentzian metric, requires a different type of structure that isn't included within this framework.
But certainly the kind of things that he's talking about are things that can be formulated on compact manifolds. There will be no boundary structure.
Only on compact manifolds.
Yeah.
No, you also smooth, right? Compact and smooth.
Yeah. I mean, smooth is taken for granted.
Nothing like asymptotic symmetries, for instance.
Yeah, which is an important notion of symmetry too.
Yeah. Yeah, so I mean, here we're confined by what the mathematicians have done in the axiomatic approach in their definitions of TFTs. What we're looking at currently, what we're working on now is, I flashed up back. I flashed up this work down here about geometric field theories, and I know there's some skepticism about this work and works related to this, but these sorts of field theories allow you to put metrics on them. So one may be able to study more generalized things in this context. These papers are incredibly new though, they're only like a year old. So the mathematics really behind these is somewhat old and somewhat new, but it's what we're currently looking at. Okay, any other questions? Yeah.
There's been like recent work on like understanding symmetries of ordinary field theories by considering like topological field theories and like boundary conditions. And so you could use this for the bulk topological field theory, and that would tell you stuff about just ordinary field theories.
You're talking about this thing where you go from a higher dimension one to a lower dimension one?
I'm thinking of like the work of Fried and Tellman.
Yeah. No, so I think that's slightly different. Yeah, if I'm aware that works about the more like defect approach to it. I haven't looked at those papers in detail, but I'm aware, I think they're more about like the defects and like back brains and stuff like that. The connection between what they have done and this approach to it versus what I've done here is not immediately obvious. I would say it's something that perhaps one needs to understand page 100 of Laurie's paper on the cupboardsum hypothesis or whatever, but it's not clear. Okay, from this. Okay, any other questions? Okay, so if you lost me in that first bit of the talk, you can rejoin. Hopefully the second bit of the talk is going to be kind of disconnected from that first bit. When I first wrote this talk, really this was the first slide. So yeah, if you did lose me through that first bit of the talk and you want to rejoin, now is a good point to do so. What the aim of this first part is to motivate that the space of TFTs really tell you that they form a category, and to define a symmetry, and to define symmetries on this using a basic, more hands-on approach. In other words, I'm going to kind of walk you through how we did it, how we consider the space of TFTs, and how we define a symmetry on it. And to do that, before that, we should ask how physicists versus how mathematicians think about symmetries. When you say the word symmetries to physicists, these sorts of words come to mind. Representations, projective representations, higher form symmetries, non-invisible symmetries, categorical symmetries. When you say symmetries to the mathematician, really they think of 3 steps. They think of a group, an action of that group, and a fixed point of the action. And this is how mathematicians, I'm of course generalizing here, but this is how mathematicians would define a symmetry. So what we're going to do is we're going to think like a mathematician, and we're going to try and define a symmetry on TFTs in this way. So let's play a game. I want you to find the symmetries of this field theory, which I'm going to call Z or C. Okay, find the symmetries. So clearly I haven't given you enough information. Maybe you'd want something like a Lagrangian, maybe you'd want a partition function to define the symmetries. But just telling you field theory said is a field theory doesn't give you nearly enough information for you to define a symmetry on it. So let me give you some information. Let me tell you that Z sits in a set with 2 other field theories, Z2 and Z3. And I'm going to ask, can you define a symmetry of a field theory just given this information? And naively, you might think the answer is no. I'm going to show you the answer is yes. The type of symmetry we're going to get is not going to be really a useful notion of a symmetry. It's not really going to be the symmetry that we as physicists think of as a symmetry, but it will give us an idea of the sorts of steps that we want to take, and the sorts of approaches that the mathematician would use to define a symmetry. So let's follow those 3 steps. Let's first choose a group. I'm going to take my favorite group, set 2, basically because I don't need to define it. And we want to choose, so that's step number 1, choose a group. Step number 2 is choose an action of that group. So let me choose an action of that group on the set, which just swaps set 2 and set 3. That is a set 2 action of that group on that set. And I can find the fixed points of that group action, and the fixed points are just this subset this subset Z. And if I wanted to, I could say that this defines a symmetry, a set 2 symmetry of the field free set. This wouldn't really be a good notion of a symmetry. It's a well-defined notion of a symmetry, it makes sense, but it's not really a good notion of a symmetry.
It's not a symmetry of Z.
Yeah, exactly. I don't understand.
It doesn't act on Z at all. It's trivial on Z.
We can put me, Sav, and Seth in a set and have a Z2 symmetry.
Exactly.
that
Yeah.
swaps us. That doesn't mean Seth.
No,
has
yeah.
Z2
I agree.
Badly broken.
I agree. No, I agree. This is not a good notion of a symmetry, right? It's an archaic notion of a symmetry. It doesn't really make sense. It's well defined. I can do it. There's nothing wrong with this definition of symmetry. It's just not what we as physicists think of as symmetry. Yeah.
But you want the group to act on the object that has the symmetry, right? I mean, it's acting on X though, and not Z. I think that's the conceptual.
Yeah, right. So the symmetry here, yes, maybe the symmetry, the action of that symmetry is always going to be on X.
Yeah.
It's always going to be on the object that we put around the field theory. It's not going to be on the field theory itself. The notion of the fixed point is really what the symmetry is. Hopefully this will become clearer as I go on.
I'd also say that in physics, we're really not interested in symmetries in general. We're interested in symmetries that preserve some structure, that commute with the Hamiltonian, that commute with some other set of operators, that preserve some structure that we demand physically.
Yeah.
Just some exchanging two things that might not have any properties in similar, no properties in common, is not interesting for physics.
I agree. I totally agree. So yeah, my point is,
So perhaps we can have some real examples. Can we go a little faster, have some real examples?
okay. Okay, the point is that this is not a useful definition of symmetry. Okay? It's the steps that one can take to define a symmetry. You can follow those steps, but it's not a useful definition of symmetry. So we've learned something, and the thing that we've learned is that it's not useful to consider field theories as forming a set. That information, as we pointed out, and has been clearly made, that does not give us a well-defined notion of a symmetry. It's just an arbitrary way that one can define a symmetry. So let me give you a different set of information. Let me give you a field theory set. And now, you have a field theory set and you have a bunch of maps between it. And these maps can be structure preserving. They can be those maps that commute with the Hamiltonian. So for example, if your field theory had Lagrangian, it could be certain, or had a Hamiltonian, it could be the sorts of maps that commute with the Hamiltonian, if you wanted. And we can say that these maps form a set, alpha I. And if I asked you to define a symmetry in this way, perhaps you would still struggle. Because I haven't told you what you can do with these maps. I haven't told you that you can compose them or that you can take an inverse. So let me tell you that this set of alpha i's, they form a group. So then you can compose them, you can take an inverse, and you can do all of these sorts of things. And this is really perhaps closer to the physics definition of a symmetry, where you have Lagrangian, and you can act on your fields, and you can move them around, you can perhaps act with your fields on a representation, and things like that. So this object is really the thing that's going to replace our set X. And this is called a category. It's a specific type of category called a groupoid. and really you can think of it if you want it as a topological space. So really this,
Sorry, is the category in this case like the category of all topological field theories?
So I am simplifying, but yes, it should be.
Okay.
In theory, there should be maps to other field theories.
Yeah.
As well. I'm simplifying by just considering one field theory because it's not really going to matter for what I'm going to say.
But coming back to something that Jeff brought up, I mean, do you demand that your automorphisms actually act on something? Do they actually do anything? Or could it be that all of these alphas just do nothing because
They
where's the faithfulness part? Where's the fact that it acts non-trivially in some way?
right. These alphas are defined, as we talked about before, they're defined through these natural transformations. They're defined as maps of things like Hilbert spaces such that it commutes with Hamiltonian. If it's, they have to, like, there is a well-defined definition of these, I would say, which comes from,
Which somehow implies that it's not trivial. I mean, we don't want to be in a
Yeah.
situation where we say that the standard model has monster groups. And
Exactly,
stuff, but it
yeah.
all acts trivially on every field.
these are defined to be certain objects. I mean, this definition includes a set of objects, right? It's like if you said, what is an example if Z was represented by a Hilbert space, a vector space, you could ask what are the symmetries, what are these alphas for the Hilbert space, and it's just going to be the linear maps that take the vector space to itself, the vertical linear maps that take the vector space to itself. So I would say the definition of this Z and the alphas, it kind of is there in the structure, and they're not going to be trivial in a sense.
Would you demand that it be the space of all unitaries on the Hilbert space so that you
Yeah, no,
measure
so-
norms? And then there are actually different definitions of what U of a Hilbert space is?
Yeah, so there's no these are not unitary. We're gonna, part of the definition of field theory, or part of the understanding of the field theory is no notion of unitarity. This will hopefully become clearer in the second talk, but we're not gonna, we have no unitarity constraints on these field theories. But in theory, in a physical Hamiltonian picture of quantum mechanics, for example, you would just take the unitary operators that commute with the Hamiltonian would be these alphas. If that makes sense. Yeah.
If I just consider quantum mechanics, could you like use this to prove Wigner's theorem in some different way? Or?
Why don't we let Joe tell us about what he wants to tell us about, and you can ask about interesting applications later.
Okay. So yeah, we can define a symmetry. We can start with this object as our basis, and we can ask, can we define a symmetry in this way? So we can ask the question, is a symmetry of a field theory just a homomorphism from G towards Z? So that's like a naive notion. It's like perhaps the first guess of a symmetry. And if one does this, what we would end up with, or I should say this is kind of a good notion of a symmetry, it would give you this idea, trivial actions. Because we haven't gone through the steps that a mathematician would go through in defining a symmetry, we kind of just jump to the conclusion. So let me go through how we would define a symmetry on this object. And hopefully it should be clearer than what I mean. So first of all, we choose a group. The title of this second section is called abstract nonsense. So let me be fairly abstract and call it group G. We want to choose an action of that group. So we want to choose an action on this whole thing here. Okay, so like we chose an action on the set X, here we want to choose an action on this groupoid, this whole structure. So the only thing we can really do is we can move the alphas around. In other words, we can somehow, for each little g in the group G, we can somehow act on our alphas to move them around. We want to do this in a way which doesn't muck up composition or inversions or the identity. We want to do it in a way that's consistent. And for that, we need F to be, this is a bit of a mouthful, a homomorphism from G to the automorphisms of the automorphisms of Z, where the automorphisms of Z are these alphas, and this bit means that we don't muck up the composition or their inversion. So this is going to be our definition of a group action. And really what we want to do now Oh, sorry, and to the mathematicians, this is really the structure, or what they would call a two-functor. So this data here together forms a two-functor.
I have a question. I mean,
Yeah.
So I understand if there's a group Z, I know what it means to have an automorphism of that
Yeah.
automorphism. But I don't understand yet what the actual definition of Z is. I mean, what do these maps alpha have to satisfy? How are they defined?
Okay.
If I give you a specific topological field theory, how would you compute what the alphas are?
Okay.
I don't know how Z is defined.
Yeah. Okay. Let me give a very quick definition. So this C. So okay, on a field theory, this C. This is kind of what I was talking to with Clay earlier. It can act on certain spaces. So if this was a one-dimensional field theory, it can act on, for example, the empty set, and that will give you some vector space. Oh, well, okay, on the empty set, it's just going to give you C. It can act on a point, that's going to give you a vector space. It can act on 2 points, so really that's going to give you phi equals phi, and so on and so forth. So this is kind of what the definition of a field theory, a topological field theory is. And what these alphas are is they are maps from the field theory back to itself. And what this really means is that for each space-time point, or for each of these vector spaces, you've got a linear map between them. And so let me call this linear map alpha dot. And this has to obey a condition. Let me just do an example. So this has to obey a condition, a commutated diagram that looks something like this. And this diagram is basically a diagram which is time evolution. So you could put any sort of time evolution here, any sort of manifold with boundary that has this as one boundary and that as another boundary, and this diagram has to commute.
So is it just GLV?
Yes. Yes, it is. For this
So
specific example.
whatever the V is that it assigns to a point,
Yeah.
odd Z is just GLV.
Yes. Yes. This will become clear in a second as I talk. And then in higher dimensions, it's more general versions of this.
I don't understand why we have aught of Z. Why don't we just have G into aught of Z?
So G into aught of C.
Why don't we just have that?
So this will give you there's no action here. This is like the trivial action.
Why? Aught of Z acts on the field theory. So why is G, why would embedding G into aught Z not?
Okay, let me just give if I give the next slide, I hope this might answer the question. So the next part is the fixed points. And really the fixed points is the information of the field theory with the symmetry. So the fixed points here are maps M from G to aught Z, which satisfy this condition. So this is like a homomorphism condition, but it's slightly twisted in a sense. It's twisted by this f of G. So if you let f of G be the identity, the trivial map, then this just becomes a homomorphism, and this gets back your case. Let me skip there. And really, it's the combination of Z and this map M, which is the field theory with the G symmetry. So your example, if you just let M be a homomorphism from G to aught Z,
Let me ask, suppose there is no higher form symmetry in the problem at all.
there is no higher way, yeah, okay.
Then does F have to be the identity?
No. So
What's an example where F is not the identity?
the projective representations. Or antilinear representations. So projective representations, F is not the identity here. It's some sort of inner automorphism which moves it around.
Sorry, you're imagining that. Okay, can you unpack that example? I don't fully understand.
This is the last part of my talk, is doing this example. But do you want me to explain it now, or?
Go ahead. You can keep going.
Okay.
Go later.
Yeah, so this notion, this definition of a fixed point is really the definition of a two-natural transformation. And this is what gives you projective representations, and we'll see this in the last sub-talk about what projective representation is, how you get projective representations from this. Then the next question is, I should say that to the mathematician, all of these constructions are completely natural, although they're perhaps ad hoc here. I've constructed them in a slightly unusual way. If I was giving this talk to a group of mathematicians, it would really just be take your category of TFTs to find the natural notion of a group action on that category and take the fixed points. Okay, so then we can ask the question, what about generalized symmetries, which are defined through non-trivial actions of topological groups? And to do that, you need to look at higher categories. So not just categories, but with these alphas, but also morphisms between the alphas themselves, and then arrows between the arrows of arrows, and so on and so forth. I'm not going to go into detail about this, just because it's slightly more technical. Okay, so that kind of ends the second sub-talk. Let me just give the three takeaway points that for a mathematician, a symmetry is defined by a group, an action of that group, and a fixed point. Field theories live in categories. This is kind of the right notion to define a field theory because it gives you not only the field theories themselves, but the morphisms between them, and you can recover higher form symmetries using higher category theory. Okay, so, might not be known, but by some of you in the audience, but Saunders MacLean, one of the founders of category theory, was actually here at the University of Chicago. He actually came here, although he never actually applied, he kind of just turned up and then was admitted. And he also coined this term called the nodal lemma, which is perhaps one of the most famous and most useful theorems or lemmas in category theory. So that kind of ends the second sub-talk. I'm going to go into the first sub-talk where we're actually going to look at an example. We're going to do basically quantum mechanics, and hopefully some of these more abstract ideas will be more apparent in this sense. But does anyone have any other questions before we do that? Yeah.
Small question. You said that when you're writing it as a two functor, you're thinking of like de-looping the group twice. Is that?
Not twice, just once. I'm taking BG.
But BG is a one category, right?
Yeah, yes, BG with trivial two morphisms.
Okay.
Or if it's a topological group, just BG, and it can have higher higher non-trivial two morphisms, but BG of some topological group. Okay, so let's go back to undergrad. Let me give you a concrete example here of the sorts of ideas that we can have, or these sorts of ideas. I'm going to try and explain the symmetries of quantum mechanical like theories, and really the aim of this is to understand the symmetries of quantum mechanics. So when a mathematician says understand, what they really mean by that is classify. So we want to classify the symmetries of quantum mechanics. And if you want to classify the symmetries of quantum mechanics, the first thing we want to do is we want a classification of all quantum mechanical systems. And if you ask this question, what is the classification of all quantum mechanical systems? The answer that I can give is that I have no idea. So really this problem is no starter. You can't really do this problem with quantum mechanical systems. And this is a motivation for using topological field theory.
Sorry, wouldn't we say that quantum mechanics is a Hilbert space and a Hamiltonian?
Yes.
And any Hilbert space and any Hamiltonian is allowed? So
Yeah.
what is wrong with?
Yeah, I guess. I mean, okay, you can do this for 1D. You can't do it for 2D. 2 plus 1D. Well, no, 2D.
Isn't the definition of like what quantum mechanics is? It's like you have a Hilbert space.
Yeah, I guess what I mean,
Right.
what I mean is slightly more intrinsic, is that we know what the space of TFTs is. We know we can classify this simply. We know all of its structures. As far as I'm aware, you can't do the same for quantum mechanics. So you can't play, we don't know the topological, so for topological field theories, we know this space, at least in some examples, but we just don't know the space of quantum mechanics. We don't know the number of inequivalent quantum mechanical systems, for example. At least I'm not aware of it.
There's some uncountable set, presumably. There's some.
Yeah, it probably is some uncountable thing.
When you say quantum mechanics, do you have in mind ordinary undergraduate non-relativistic quantum mechanics? Because after all, quantum field theory is quantum mechanics.
Yeah.
So quantum mechanics with an infinite number of degrees of freedom.
Yeah, I mean quantum mechanics. I'm gonna ask this let's just. I'm gonna go to topological field theories in a second anyway. So we are gonna throw away this structure and we're gonna go to topological field theories. So yeah, let me just skip this and say, okay, to define quantum mechanics, we require a metric. So we wanna do this problem if we wanna classify the symmetries of quantum field theory, we need to throw away the metric. And that gives us what I've defined here as a definition of topological field theory. So let me ask the same question. So let's, instead of working with quantum mechanics, let's work with topological field theories. And then let me ask the question, what is the classification of all topological quantum mechanical systems? And then the answer to this question is perhaps easier to know. It is there is one for each natural number n. So for each natural number, say 1 or 7, there is one topological field theory, and that field theory is unique. And this natural number just corresponds to the dimension, if I go back, of this vector space phi, or the vector space that I've written down there. There is one unique field theory for each dimension of Hilbert space. Okay? To the mathematicians would say that the category of TFTs is equivalent to the category of vector spaces with isomorphism between them. So we can play exactly the same game that I played in the first subtalk. We can ask, can we find the symmetries of this field theory? And of course, I haven't given you enough information. I need to give you those maps. And as has been mentioned earlier, those maps are here for this example, just the different ways that you can take a vector space and map it to itself out to inversion. There's no notion of unitarity here, so it's not like I'm looking at UN. It's just those maps which are invertible that take the vector space that you can act on a Hilbert space, take it to itself, and back again. Okay, so this is all matrices which are invertible. So we can ask, what is the group action in this case? So let's first choose a group. Let me be abstract and take that group to be G. We want to choose an action of that group on this space. So we call an action, takes this groupoid and maps it to itself, like this. And it maps it to itself using these f of g's, which we can choose. And in this case, f must be a homomorphism from G to the automorphisms of GLN. Okay, so this is just an application, it's just a specific example of that first case of what we looked at in the second subtalk. If we want to classify all symmetries, if we want to classify all actions, then we need to know what this automorphism group is. And it turns out that this automorphism group is known, and it allows us to do this classification. So given that this automorphism group is known, we can find all homomorphisms from an arbitrary group G into it. That allows us to find all group actions, and then we can find the fixed points. So let me give you an explicit example. Let me choose a group. Let me still be abstract and choose that group G. And let me choose an action of that group, which factors through the inner automorphisms of the automorphisms of G, Ln. In other words, I want to take f of G on M to be something like this for some UG.
So you're choosing a group and a representation of the group? What is M?
M is, sorry, yes.
Is N the dimension of a representation of G?
N.
Little n.
Yeah, N is, yes, the dimension of the vector space my TQFT corresponds to. In other words, it's the dimension of the.
You've got a map from elements of G to GLV, so a representation of G.
No, at this stage, I've got a map from G to the automorphisms of GLN. So remember, this is that group action. It's not yet the fixed points.
But don't I need to know how G acts on V to get?
Yeah, so this is going to come in a second. So this is the third part, right? So remember, we had the group, we had an action of that group, and then we had the fixed points. This group, the action of the group is the step before we find how that group acts on the actual vector space.
I guess this action might be completely trivial because there just might not be a non-trivial action on GLNC for some n.
I mean, there is always inner automorphisms.
Well,
But yes, it might be trivial.
Yeah, which contain the identity. And
It might be trivial. It might be
It
trivial.
might be that the only way you can make G act is to act trivially.
Yes, I agree. So what this corresponds to in terms of this diagram is you take your what I used to call alphas, which now I call M, and you map them to itself, or where you've got complex conjugate, or where you've got conjugation by an element there. So this is an action. We've chosen the group. We've chosen the action of the group. Remember, the physics content here is the field theory itself plus the fixed point. So it's the definition of a fixed point. So let's try and find the fixed points in this case. Remember, I defined a fixed point to be a map M from G to GLN, which satisfies this kind of twisted multiplication rule. If we sub our definition of f of g into there, we get this equation here. Okay? So this is just purely definitions at this point. I'm going to then do a series of algebraic manipulations, and this is just like a redefinition of m prime. And you get this sort of structure down here, where m prime is defined here, and this thing I know to be in the center of G supercommutes, and you get this thing down here. So this is just a projective representation. Right? So the physics that we have found here is that this group action that vectors through the inner automorphisms, the fixed points of that group action are projective representations. They are the projective representations that you find in quantum mechanics to define things like the rotation of an electron. Yeah,
but you don't know that the projective representation is non-trivial until epsilon is shown to obey some cocycle.
Yes,
It has to be non-trivial in H2.
Yeah. You can get any.
So you may be able to reabsorb that epsilon.
Yes, I agree. I agree.
More information than this.
I agree. This is not here, but in the paper you can see that any epsilon for which there exists a projective representation of this given G will appear.
I mean, any G for which whether or not there's a projective representation depends on the group G.
Yes, it depends on, N is fixed, so it depends on G and N. And the question, it depends on, so here we have the group G, we have the dimension of the vector space N, and we have an epsilon. So there may or may not exist a projective representation of G with cocycle epsilon of dimension N. That's possible. If there is a representation of G with this cocycle, then it's good. Then we know it will appear here. But yeah, I agree. This could be non-trivial. It could be trivial. It could be anything. Does that make sense?
Well, I thought you could determine whether there were non-trivial projective representations without the data you're calling little n. I thought you could just compute H2 of G with U1 coefficients, and if it was non-trivial, then you knew there were non-trivial projective representations, and if it was trivial, there weren't. And I didn't think it depended on
Yeah. I guess I'm asking a different
any more
question.
data.
Yeah, I think what you're saying is true, that if you have an epsilon, then you can determine if there are these representations. If you have an epsilon, the extra bit of information, the extra constraint, let's say, that I have here is that I fixed an n, and I don't know there might not be a projective representation with a given epsilon for that n. It may not exist. I mean, yeah, in general, for 1D representations, if epsilon is non-trivial, there are no alphas. So yeah, this gives us projective representations. And let me just give you, before I finish, all of the automorphisms of GLNC, and these are them down here. They're classified with these sorts of things. So we can ask, what are the fixed points, and what is the physics behind them? So this first case, m goes to m, which is just the trivial case. So in other words, the case that Clay was talking about earlier, where G goes to the automorphisms of GLN, that just corresponds to here, just representations. It's just a homomorphism from G to GLN. This inner automorphism one, as we just showed, corresponds to projective representations. So we know we see all of these in physics or quantum mechanics. M goes to M star. This has got a name. It's something called a semi-linear representation. M goes to M minus T. I don't really have a name for this, but you can write down the group law at Master Bay, and then M goes to the determinant of M. Again, I don't have a name for it. And we can ask, where do these occur in physics? Hopefully, the fact that representations appear in quantum mechanics is obvious, and that they are symmetries of quantum mechanics is obvious. Projective representations come in with, for example, the rotation of an electron. Semi-linear representations are related to time reversal. This M goes to M minus T, which is related to orientation. I should say that this is not necessarily the same as this, because we're not restricting ourselves to unitary matrices. And I'm not aware of any physics that involves this M goes to the determinant of M. So yeah, this kind of classifies every type of symmetry you could have in a quantum mechanical system. And without doing an analysis like this, you may just say, okay, you have representations, you have projective representations. You may guess you also have semi-linear representations, but to find things like this, and perhaps like this, requires a more concrete analysis. And to say that they are the only types of symmetries that you could possibly have needs a concrete, well-defined analysis.
Is it, when you look at automorphisms of GLNC, is there some demand of continuity?
No. Every case is an
I
abstract.
don't think the set of all automorphisms of C are known if you don't impose continuity. If you impose continuity, then I think it's complex conjugation of the identity, but if you don't demand continuity, I think there can be very weird things.
Yeah, sorry, I've been slightly naughty here. That I put M star, and what by M star I mean any field automorphism of C star. So that's where this complaint comes in.
But I don't think any of those are known to appear in any physical context.
No. Yeah, okay. But if you want a group, yeah, I agree. This depends on in the automorphisms of C star or K star in a generic field, just because of this one here, where this star is.
Well, if we were doing quantum mechanics over some field other than C, then it would be relevant.
Yeah. I mean, yeah, all of this rule here is actually generic for any field. But complex conjugation up to, it's the only one which is of order 2. All of the others are of order infinity anyway. So you could argue whether a G into that's going to be particularly useful, just because you're going to get like an infinite group. Okay, so let me summarize the key points of this. Firstly, finding symmetries of field theories is somewhat easy, especially if you know what the space of topological field theories is. I gave you here that they were classified by this number n, and then GLNC was these maps between them. In 1D, you have representations, projective representations, semi-linear representations, and other things. And then you can also do the same thing, the whole analysis that I've just given you, classify the symmetries of 2D field theories. One could do the same with any dimension field theories. The difficulty is finding the space of topological field theories or the space of field theories. And once that is known, this whole analysis to the mathematician to the homotopy theorist is really relatively easy. Okay, so that ends the talk. And yeah, if you have any questions or comments, great.
In the second last slide, you had the table on the left. That's from Dudon's theorem for the GLN action, or like how did you know there were only like what 5 of them?
These.
Yeah.
This comes from the classification of this. So this automorphism of GLN, it's known that the only things that you can get are these here, and then combinations of these, and that's it. So there's no other automorphism of GLN which doesn't fall into one of those 5 categories or combinations of those 5 categories.
If you demand unitarity, does the last one go away, or?
That was the question I was going to ask.
Well, what about the second to last one? I also don't understand what that is.
That becomes
Yeah,
equivalent.
Yeah, so the second last one, the unitarity becomes the same as this one.
But there's the last one.
Yeah, I don't know. If it's symmetry, is the determinant of M of unitary matrix just 1 or minus 1, or is that?
No.
It's
It's
M
any
through base,
complex
right?
number.
Yeah, I guess it just becomes,
Yeah, any complex space.
yeah, I don't know.
So then maybe you can put it into the UMU diagram.
Yeah, maybe it's just gonna generate.
Into the first 2 maybe.
You're
The
asking,
second and third.
asking if this just becomes a combination of things of that?
Yeah,
Maybe.
once you demand that dimension.
Can you get a phase by an inner automorphism? No, I don't think so. I mean, this is going to be multiplication by a phase, right? And it's a very specific phase. And it's not the same phase, so it's not the same phase for each matrix.
Yeah, that's true.
Yeah, so it's a bit, I mean, okay, let me put it another way. This is the only one of these where it's M appears twice. All of those M appears once. Yeah, I don't know, yeah. I don't know about this last one. It might drop out if you add continuity. If you add that, yeah, these things must actually be, instead of what I've been considering here as abstract groups, if you add the condition that they must be smooth groups and all of these things must obey smoothness conditions, it may be that this last one falls out, doesn't work, doesn't count.
So it's a general question. So
Yeah.
I have to say that the first time I saw your paper, I thought it has something to do with phenomenology. Because your advisor has done phenomenology.
Yeah.
So do you have anything, am I missing it, or do you have anything that has something to do with the real physics example?
The short answer is no. I would say this is as close to physics as we get. There's no proper phenomenology in there. It's yeah, I would say it's not really just because these TFTs are so formally defined and they're so far from physics. It's hard to write down like an example that physicists would go like, oh, okay, this is this theory with this Lagrangian, etc. That answers the question.
Not even Lagrangian, but any statement. Any physical system.
No, it's just because these field theories, I mean, I say this is the first step down a road, and this first step is defined on these very simple field theories where you don't have any structure on your space-time. There's no metric, there's nothing, there's no like spin structure, there's no Riemannian metric, there's nothing like that. So to write down, a physical example which is not completely straightforward, you can do digraph Witten in this sense. And that's basically, I would say, one of the only theories that you do that the physicists perhaps would know. So like finite gauge theories.
Surely there are many more topological field theories than that. Perhaps the most famous is Chern-Simons theory.
Yeah, but I don't think Chern-Simons theory can fit in this framework unless I'm wrong about that. You require like a Lagrangian with a connection or not.
That is the definition, but the output is a semi-simple topological field theory.
Yeah.
So yes, I think it does fit in.
Okay.
You've done this as far as 2 dimensions. And what's the obstruction to?
The obstruction is not anything I talked about here. It's really just writing down this space of TFTs. So yeah, we just don't know the space of 3D TFTs. If you know that, you can do this. This is easy. I guess it's the thing. It's not really, the difficulty is not with this part. It's really classifying the 3D topological field theories and classifying this space of field theories in 3D and higher. Yeah. Otherwise, it's just everything here just works and follows.
In the case of like having G, N and some cocycle, or like what is the obstruction to the existence of cocycle for a given number N?
So it's not the obstruction to a cocycle existing. It's the obstruction to a representation existing. So go back. So there may not be a set of matrices that satisfy it. There may not be an M which satisfies this condition. It's the obstruction. In other words, there might just not be, the statement I'm saying is just that given a cocycle, defining a projective representation, and the dimension, there might not be a projective representation of that dimension with that cocycle. This is not true for representations because representations have, for any dimension, you have a representation of that group. It's just a trivial representation. This isn't true for cocycle. This isn't true for projective representations. Projective representations exist only at given dimensions.
Could you give some examples where like it fails, or like
for
is there
instance,
something
there's
that's
no
nice?
such thing as a one-dimensional projective
Yeah.
representation.
Yeah, okay, I guess that's.
Yeah.
Or for instance, you could think about even versus odd dimensional representations of SU2/SO3.
Let's thank Joe again.